Good morning everybody, I am Vedant Salphale, student of 8th semester Aeronautical Engineering at University Department of Rajasthan Technical University. Feel elated to present my seminar presentation titled Flying the Aircraft, a Futuristic Approach under the guidance of Sir Anshul Khandelwal. I would also like to thank our seminar coordinators Sirs S.S. Godara and Sir D.P. Sharma. So let's begin with the outline. The presentation includes introduction of topic, experiment and comparison with reference aircraft, aerodynamics of flying V, structure of flying V and passenger evacuation analysis. First, introduction. This is the brainchild of Justus Bernard, who pursued this idea during his internship at Airbus Hamburg in 2014. The flying V aircraft is a futuristic shape of aircraft. As the name suggests, it looks like the alphabet V. The passenger cabin, cargo holds and fuel tanks are integrated in the wings itself, and the engines are placed near the trailing edge. Next, the experiment. A radio-controlled 22.5 kg and 3 meter scaled model of Flying V was tested in July 2020. The mission of the model was to take off, perform several test maneuvers, and when the batteries are almost empty, land. The test results were used to compare various characteristics of Flying V with presently operating commercial aircrafts. The benefits over the reference in terms of aerodynamics were 10% higher L/D ratio or the lift-by-drag ratio and 2% lower structural mass. Next, the aerodynamics of Flying V. Flying V aircraft is a tailless aircraft with two cylindrical pressurized cabins placed in the wing leading edge and two engines over the wings. The objective of this innovative concept was to achieve highest lift-to-drag ratio and lowest empty weight. A software named Odila 3D lattice vortex technique was employed to analyze the aerodynamics of Flying V. The program was used to optimize the wings twist for maximum performance in cruise flight with Mach number 0.85 at FL 360, as well as to anticipate drag, lift distribution and neutral point. The platform was created in such a way that the lift distribution is vertically elliptical during trimmed cruise flight and the neutral point is behind the center of gravity, allowing for longitudinal stability. Ailerons on the wing trailing edge provide longitudinal and lateral control, while the winglets serve as the aerodynamic design. The inner portion span is limited to 26 meters by the maximum acceleration that passengers may tolerate. The aircraft span is limited to 65 meters by the gate restriction. The sweep angle is set to 63 degrees. Over the trailing edge of the wing are two turbofan engines, as shown in the figure. Effect of engine location. Engine location plays a crucial role in aerodynamics of an aircraft. The goal was to determine an appropriate placement and orientation for the Flying V twin turbofan engines. The reference area was chosen to be 895 meters square and was used, and all aerodynamic coefficients reported were rendered non-dimensional. The thrust produced by the A350 engines was equal to 50 kN each. The engine simulations were performed using standard nacelle geometry. A set of CFD Euler simulations were done using the commercial solver ANSYS Fluent to study the aerodynamic behavior of the Flying V with and without the engines. A second-order discretization and a pressure-based implicit solver were used. Every simulation was run using just half of the Flying V model and applying a symmetry constraint. All simulations were run using a rectangular domain as shown in the figure. A pressure boundary was established on the far field with cruising condition of height 13,000 meter and Mach number 0.85. Next is the validation. Validating the result was difficult because of lack of available data. The results were then verified by comparing to previous studies without engines and analytical approximations. The major goal was to figure out how the engine position affects the lift-to-drag ratio. The simulations were performed using Fluent and SU2 software, and data was compared as shown in the table. It was found that placement of nacelle plays significant role on aerodynamics, and misplacing it can lower the L/D ratio by 55%. Next, Effect of rudder deflection and winglet integration. A 4.6% scaled half-wing wind tunnel model was used to identify winglet integration effects on the flying V aircraft. The winglet integration improved the lift coefficient by a maximum of approximately 0.0035 for angle of attack below 10 degree and slightly reduced the lift coefficient by a maximum of about 0.016 for higher angles. The winglet increased the model's drag by a maximum of 0.004 until the angle of attack reached around 28 degrees. At 10 degree angle of attack, the winglet lowered the maximum untrimmed lift to drag ratio from 14.4 to 12.3. Winglet increased yawing movement of lift wing between 2.5 and 20 angle of attack. Almost all rudder deflections have been shown to diminish the lift coefficient at all angle of attack, with the left wing reducing the lift coefficient by a greatest amount about 0.0024. The highest change in side force coefficient due to rudder deflection on one wing was approximately 0.008. Positive rudder deflections enhance pitching movement more than negative deflections. Due to one rudder, the greatest increase in the aircraft's pitching movement is roughly 0.0035. The side force, yawing movement and rolling movement were reduced by 49%, 50% and 37% respectively. Next, optimization. The aim is to increase efficiency. MDO multidisciplinary design optimization is employed. Since CFD and FEM cannot be employed because they are expensive and time-taking computations, the ultimate load factor is the most important consideration. The cruising phase performance and the maximum lift coefficient were the data required. The resulting values of M star were 0.90 for the inner wing and 0.93 for the outer wing, close to the value of 0.935 stated in previous studies. The zero lift drag CD0 must be approximated using analytical methods. Two essential aspects in the validation of the aerodynamic calculations for the zero lift drag and the Oswald factor test was conducted at Mach 0.85 and Reynolds number 30 million. As a result, the wind tunnel data is compared to the CD0 of the modeled aircraft without these effects. The zero lift drag was verified with the result of 123 drag counts for the wind tunnel test versus 119 drag counts for the model. Oswald factor was found to be 0.753, very close to 0.75 that of A359 model. The images shows the optimized design platform overlaid on the baseline design platform and the cabin interior is visualized. The elevons are housed in the outer wing which also serve as stabilizing load. The optimized version's narrower cabin is compensated by its length in order to accommodate the same cargo as the baseline variant. The optimized form has a greater thrust to weight ratio than the baseline variant. Next is structure. The flying wing structure concept is based on existing structure of other flying wing aircrafts. An oval cross-section fuselage was introduced instead of circular. The aerofoil is fitted around the fuselage perpendicular to the leading edge. The second cargo cylinder is fitted into the airfoil by featuring a shorter radius. The aerofoil ribs are attached to the inboard half of the oval fuselage. The inboard arc is eliminated and the primary shear web is replaced by the inboard wall, as shown in the figure. Fuselage sweep transition. The fuselage lock between section 2 and 3 is known as the fuselage sweep transition as seen in the figure. The front fab is constructed by projecting the outboard wall's front edge onto the root and producing a shell in between. The top and bottom oval shells as well as the ceiling, floor and inboard wall all have similar root plane connections. To retain an open cabin idea without structure members limiting space use, the front fab has a cutout. Next is fuselage-to-wing transition. The goal is to connect fuselage and wing sections, major structure and transmit loads between them. The fuselage front oval arc and rear cabin wall must be attached to the front and rear wing spars respectively. Ribs with cutouts run the length of fuselage, connecting the cabin to the wing box of transition main structure. Additional frames may be inserted to increase rigidity. The ribs are evenly spaced from the end of the pressure cabin. The ribs are positioned so that the front and aft spars are separated into equal span portions outboard of the kink rib. Next is fuel tanks placement. Fuel tanks are one of the heaviest components on an aircraft. The Flying V design offers several fuel tank location choices, as can be seen in the figures. Large fuel quantities may be found in the following locations: the transition wing box, trailing edge, aft and inboard of the fuselage. Next is passenger evacuation analysis. Since the cabin design differs dramatically from standard aircrafts, it's necessary to analyze the evacuation of passengers in emergency conditions. A simulation program based on the concept of cellular automata with a floor field model was created. The passenger cabin was observable domain, represented by a grid of square cells. The size of each cell was set at 40 cm by 40 cm. All passengers in the early model moved at the same speed of 1.3 meter per second. In the current simulation, a passenger moved one cell each time step, resulting in a time step of about 0.3 seconds. When a passenger exits through an exit door, they are deemed evacuated and will be disregarded in the following time step. For the Flying V and the reference aircraft, various closed-door designs were investigated. Since these are preliminary results achieved with a basic instrument, extreme caution is advised with quantitative values. Nonetheless, the results suggest that the shorter V-shaped cabin has certain advantages over the longer tube cabin when the evacuation is limited to the front or rear of the aircraft, to section 5 and 6. Preliminary tool revealed a 62% reduction in evacuation time for the Flying V when half of the doors in the front of the aircraft are closed, section 5. A reduction of 34% in evacuation time was realized when half of doors in the back of aircraft were closed. When passengers in the V-shaped cabin must evacuate just to one side, there may be difficulties in the evacuation process. These images show evacuation comparison with the Airbus A350. Next is conclusions. The Flying V design of aircraft is still at the conceptual phase and various areas are still being explored. Advantages over reference aircraft are as follows: 10% higher lift-to-drag ratio, 2% lower empty mass, no high lift devices, fairings and less parts, lower sound and engine shielding from ground, elliptic lift distribution in a naturally stable design, and smaller length. Since everything cannot be perfect, there also exist some disadvantages with the Flying V. These are as follows: exhibition of Dutch roll mode, higher emissions than presently operating aircrafts, higher evacuation time than reference aircraft, which is a thing of concern from a safety point of view. More studies are being done in order to optimize these points and to take the Flying V design near to perfection, and it can be expected to be operational in the upcoming 10 to 15 years. These are my references. Thank you.